Okay, we got the first problem, we got three forces. Okay. So we got three forces like this, and we want to find out what the total of the three forces gives us, and then what force we need to balance the three. Okay, well, I'm not going to write out all the equations and stuff. I'm just going to represent this by pictures. This force is equivalent to this and this. So I'll just go ahead and draw this force in blue, but then I'm going to cross it out. Not cross it out so I can't still read it, because I would need these numbers to calculate these components. But we understand that this component is going to be 5 newtons times the cosine of 37 degrees, and this component is 5 newtons times the sine of 37 degrees. Similarly, for this vector, we get this component and this component again. This component is 10 newtons times the cosine of 127 degrees. Or if you want, you say, well, if that's 127 degrees, then this is 53 degrees, so it'd be minus 10 newtons times the cosine of 53 degrees. There are times when you want to do that. In this course, probably not many, but your book kind of tells you to do that, okay? Because there's some finer points of inverse cosines and tangents and stuff like that that kind of get in the way. Okay, so anyhow, in this one it's 10 newtons times the sine of 127 degrees. And then we'll make this one green. So here's 233 degrees. And of course then we get a vector here and a vector here. And we lightly cross that one out just like we neglected to do here. So now what do we have? We have, get my color straight here. So we have this. And this. I think this company know how to make good chalk. Probably a supply chain problem. Okay. Of course, there's no supply chain problem back when this chalk was made. So we have these three forces, right? And this one and this one are pretty much opposite. So the result in this direction I'm hunting for the color I want. Where this stuff all goes. We'll use this vector may be a little longer than this one, the way I've got it drawn. So maybe the resultant something wrong with these people. What in the world? Here we go. there's your resultant X force, and your resultant Y force is going to be this. And this. And this. Now do this plus this, it's going to be up about there, it's going to be about that long. Again, it might come out pretty close to zero the way I got it drawn, but let's just say get the result when you add these. Is this, and that resultant Y force is 5 newtons times the sine of 37 degrees plus 10 newtons times the sine of 127 degrees plus 20 newtons times the sine of 233 degrees. And that's going to come out 2.5 newtons plus 8 newtons. I said 2.5, that's wrong. It's 3 newtons. And then the sine of 233 degrees is negative 0.8. In other words, if we measure all the angles from the positive x-axis, we'll automatically get the right plus and minus signs. So that's going to be then minus 16 newtons. And actually, if the thing is calculated, we end up with negative 5 newtons. Resultant X force is, I'm just going to write it, well, okay, it's 5 newtons cosine of 37 degrees plus 10 newtons cosine of 127 degrees, sorry. That's degrees, not a square. Okay, plus 20 newtons times the cosine of 233 degrees. And if I do my arithmetic correctly, this is going to come out 4 newtons plus minus 6 newtons, because the cosine of 27 degrees is negative 0.6. And then minus 12 newtons. I didn't do a very good scale drawing of this, but I didn't really try to, okay? So according to my scale drawing, it looks like these things add up pretty close to 0, but that's not the case. These two negatives add up to quite a bit more than this positive, and we get negative 14 newtons. And basically this green vector is a lot longer than I drew it, if I drew this correctly. The angle should actually be more like this to give us a bigger leftward component. Anyhow, you should understand all that. And it looks like pretty much do. Okay, most of the papers saw something equivalent to this, but without the drawing. And I really prefer to see the drawing because that reinforces what you're doing, and you're not just following a formula and just solving the problem by calculation. And even if your drawing kind of sucks the way mine does, you still get the idea and you still convey the idea. Okay. So that's that. Now, next problem, you got a 20 Newton force. Probably not going to need a lot of room for this, so I'm going to try to squeeze it in over here. You got a block with a 20 Newton force, mass of 10 kilograms. and it slides 1.5 meters. So it's going to end up here, having moved 1.5 meters. Constant force starting from rest, we know that delta x is x naught plus b naught t plus 1/2 at squared. In this case, we'll assign 0 for delta x. We can always choose that. We don't have a choice on b naught, it's 0, because we start from rest. So we just have delta x equals 1/2 at squared. So t is 2 delta x over a, right? Now, you can include the rest from average velocity and so forth, but I like this reasoning. You can do it with equations, and it's easy. But the average velocity is this, which is going to be square root of a delta x over 2 and actually I'm not using the information we had. Okay. I haven't substituted for a because we don't really know what the acceleration is. Okay? After 3 seconds, it's gone 1.5 meters, right? So here t is 3 seconds, here t is 0. So now we've got 2 expressions for b bar, and we can solve for a, because we know delta x. Actually, I've been doing this in symbols, so let me stick with that for the moment. The b bar is going to be 0.5 meter per second. Still. So, that's the square root of 2 there. Square root of a delta x, so square root of 2 is delta x over t. Square root of a is then going to be it's the square root of a delta x, not the square root of a times delta x. If you do their algebra, that's straightforward. So if I divide both sides by square root of delta x, multiply by square root of 2, get A equals 2 delta x over t squared. And then that's going to be 3 meters over 3 seconds squared. So it's going to be 1/3 of a meter per second squared. Now, if I've done that right, okay. There are other ways to get to it. You can use equations and stuff, reason it out one way or another, but you get to it. And notice that we do have the right units in this. I started to make a mistake here, but I knew the units weren't going to work out, so I looked back and saw that I didn't have the square root over my delta x. Okay. Well, what acceleration would you get if there was no friction here? We get 20 newtons over 10 kilograms, which is going to give you 2 meters per second squared, right? And you only got 1/3 of a meter per second squared. Okay, so you know that there's got to be some other force, and in this case, that force is going to be the frictional force. So now you can set up an equation. And you want to do it this way because you want to do it in a way that builds to more complicated problems. Okay, so you're going to want to say you've got the 10 kilograms with a 20 Newton force and a force of friction. Net force is equal to mass times acceleration, Newton's second law. And your net force is this. Your mass is 10 kilograms. So the frictional force ends up being 20 newtons minus, I don't know where I got 10, but that, minus yeah, 10/3 of a newton. (16 2/3 newtons). Point is, you can analyze this motion to find the acceleration. Now, of course, we could have solved this. We could have solved this equation for A, and we wouldn't have to go through all this, right? Okay, so you can go to a convoluted set of reasoning when you really had it right here. If you'd have just solved this equation for A, sometimes that's going to happen, and you learn something in the process. One way or another, we get A is 1/3 of a meter per second squared if I did everything right. And if I didn't, you know how to do it. Then you just set up net force equals MA with a picture that involves the force of friction. Set that, you know, write the expression for F net, write the expression for mass and acceleration, and your force of friction comes right out. Okay. I want to move to problem 5 real quickly. That's something nobody did that you need to do. I don't think I have it there. Yeah, I do. Okay, I think this is 20 centimeters, is that right? And this is 1 meter. So that delta y equals, assume the initial y velocity is 0. Okay, because it's horizontal, now if we implicitly assume x equals 0 and y equals 0 here, then delta y is just equal to 1/2 gt squared, but it'll be, of course, negative 1/2 gt squared. And delta y from here to here is negative 1 meter equals negative 1/2 gt squared. And everybody that did this found out that t is approximately 0.45 seconds. This thing falls in 0.45 seconds. And then, kind of cutting to the chase, I'm skipping some stuff, but, because we're out of time, but, here Vx is 22 centimeters per second. Just divide the 20 centimeters by how long it takes to fall. So that much is very straightforward. So I kind of sort of went through it kind of fast. Now, in the other case, we just say, okay, we got a ramp here, and the ball goes down the ramp, and the angle was 10 degrees. Okay. So, V naught is 22 centimeters per second because we said use this for V naught. Okay? Now let's see, what's V naught x? Well, that's 22 centimeters per second times the cosine of 10 degrees. Now, the cosine of 10 degrees is like, okay, the sine of 10 degrees, we'll do the sine. I'll use the negative sine of 10 degrees. I could have used 350 degrees, which is okay. I think your book does stuff like this. It doesn't always use circular quantities. We'll do that, okay? Sine of 10 degrees is pretty close to 1/6, which is about 0.16. And I think you got about negative 3.4 centimeters per second. Now, key is you can't use 0.45 seconds anymore. Because in this case, we had 0 downward velocity at the beginning. In this case, we have a non-zero downward velocity. Okay? And let's see, cosine of 10 degrees is about 0.99. So to the extent that I rounded this off, this isn't really going to, cosine of 10 degrees is so close to 1, it's not really going to change the 22 centimeters per second. It does, but since I rounded off in that calculation anyway, it's not going to change within the round off there. Okay. So now, gotta find delta t. Here. I'll wrap this up kind of quickly. And let's assume y naught is 0. And I'll just say delta y is -1 meter again. Well, you know how to set that up. You can do it. Now t is less than your 0.45 seconds. That might still round to 0.45, but it is going to be less than what you got here. That initial downward velocity makes a difference. Thus, your delta x is no longer 20 centimeters. Now this is relevant to the experiment we did. Because in the experiment, we had a downward slope. Now the third part of that problem is where it gets hard. This is easy to do. This is really easy to do. Okay? But the third part gets pretty hard because now you got to figure out, okay, well, if it was at this angle and did go 20 centimeters, because you did observe this distance, right? Was at this angle and went 20 centimeters, what was its initial velocity? Okay, what was the V naught? And that's a whole new projectile problem you've got to set up and try to solve.